Hello, welcome back to part two of our cardiovascular system lesson from the AQA A-level PE course that we're running. This part, we're going to look at the hormonal, neural, and chemical regulation and response to exercise. So far, we've looked at health and its four components. We then went on to coronary heart disease, cholesterol, the difference between LDL and HDLs, the impact of activity and sport on fitness, in particularly the cardiac muscle itself. And then we finished off with a couple of exercises just to clarify that understanding as well as research that ejection fraction. So we're moving straight into the hormonal, neural, and chemical regulation of the heart. And we're going to start by looking at hormonal control. Okay, I want to draw your attention first off to this graph on the left-hand side where we've got a performer who has a resting heart rate of 60 beats per minute. And prior to the commencement of exercise, which was happening in 10 minutes' time, their heart rate began to climb. Okay, so it was actually beating at 100 beats per minute prior to them doing anything. And that's all down to the hormones being secreted inside of the body. In particular, adrenaline, also known as epinephrine. It's secreted by the adrenal gland, sorry, and it plays a part or it influences the neurological pathways that connect the brain to the heart. Okay, so the brain, it sends impulses in order to adjust how quickly the heart contracts. Okay, now the heart's myogenic itself, so it produces its own contraction, its own impulse, but the brain can control it's speeding up or it's slowing down. So by secreting adrenaline, the impulses which are arriving at the heart, they begin to increase in speed and quality. So we've now got faster contractions and more forceful contractions. It's also known as fight or flight, and it might be brought on by apprehension or stress or anxiety or the person thinking about exercise. But as soon as exercise is approaching and the performer knows that they're about to be doing something, is classified as this fight or flight response, and it's this body's innate way of preparing us for exercise before it's even begun. So it sort of minimizes that lag time between starting exercise and our heart catching up. So rather than our heart rate starting at 60 beats per minute and arriving at 100 beats per minute, 4 minutes into exercise, instead of that being the case, adrenaline is released, it increases the heart rate, it increases that oxygen supply to our working muscles. Well, not to our working muscles at this point, but we're filling or flooding our muscles that might be about to be used with that oxygen so that when we do start to use them, they're ready to go and we can access the aerobic system as quickly as possible. We can begin breaking down lactic acid as quickly as possible, and we're as prepared as possible for exercise or physical activity. So that's the first one, hormonal control. Adrenaline being released prior to exercise and is also termed anticipatory rise. So in anticipation of exercise, we've got this rise in heart rate from 60 up to 90, 100, 110, because our body's preparing ourselves for the exercise that's about to commence. So anticipatory rise, that's the impact of adrenaline that's being secreted on the speed and the quality of the impulses that are arriving at the heart to make sure that it beats quicker and beats stronger. There we go. So next we have vascular shunt. This is the second mechanism which our body deploys to make sure that we are as best prepared or in the best condition to be exercising as efficiently as possible. And I'll just draw your attention straight away to the pictures on the left-hand side. Now, up at the top we have a resting person. Their network is complete. There's blood flowing to all different areas of the body. Every tissue is receiving oxygenated blood. All is well. When we start to exercise, however, what we start to get are blockages or turn-offs in certain blood vessels or in the capillaries or at the joins between arteries and arterioles and capillaries. We have sphincters or precapillary sphincters in most cases. And these are rings of tissue which contract. So they might start at that sort of size, and then when we deploy the vascular shunt mechanism, the ring of tissue might start to thicken and contract, letting far less blood through to arrive at the destination beyond them. And there's many reasons for this, but primarily it's to supply the muscles that we want with as much oxygen as possible. For the areas of the body which are in higher demand, the ones which are working. So let's say a cyclist, for example, they're cycling on a bike, their quadriceps, their hamstrings, their gastrocnemiuses, they're all going to be working at high intensity. They're going to be demanding oxygen to be able to yield energy and to continue the muscular contractions. They're going to be generating or creating lots of carbon dioxide as a byproduct. They're going to be generating lactic acid. All of these impacts of exercise are being detected by the body, um, and the body reacts to this by sending more blood to it. So in that blood, there's more oxygen, and there's also more capability of removing carbon dioxide as well. So as soon as we notice, or as soon as our body notices there's a higher demand for blood during exercise in certain locations, then the vasomotor control center begins to dilate or expand the blood vessels going to those destinations. More blood will get to them. At the same time, okay, we've got lower priority tissue. So the body's constantly recording and measuring and collecting data from around our body. And it might be that if we take our cyclist again, that their gut or their intestines or their stomach, they're not being used at the moment. Okay, they're not aiding. They're not aiding muscle contractions or sporting performance. We haven't eaten for a while, so digestion has slowed down. So because it's a lower priority area, we can now restrict the flow of blood that's actually going to those areas using these precapillary sphincters. Okay, or we start to constrict the vessel walls. So instead of them being that sort of width, we start to constrict them so that less blood can flow through them. Okay, so by using these mechanisms of vasodilation, vasoconstriction, precapillary sphincters, our body shunts the blood, it pushes the blood or redirects the blood to where we need it most. It's also known as redistribution or blood redistribution. We look at our body, we work out where blood and oxygen is needed most, and we prioritize that. We shut off the blood vessels going to where we don't need it, and we open up the blood vessels where we need it most. Okay, so vascular shunt. Sorry, just going to go back. If you click on this video here in the PowerPoint, you should be able to go to a YouTube video where I describe this in a little bit more detail. So next up, we have the cardiac conduction system. So we've had hormonal control, we've had chemical control in that last slide there because we're detecting changes in chemicals and we're starting to respond. Now we have the neural control. So this is to do with the neurological pathways or the electrical impulses which our brain sends out via our nervous system and controls our body with. And the way it impacts the heart is through the cardiac conduction system. Okay, so we've got a number of components and they all work together, they all function together, and the overall result is the contraction of the heart. Okay, but the timing is essential because we obviously have lots of different components of the heart or chambers of the heart, and we don't want all of them contracting at the same time. Okay, it's known as a dual action pump because the right hand side is working, pumping blood up to the lungs, and the left hand side of the heart is working to eject blood to the rest of the body. But it's both happening at the same time. So we'll start from the top where I mentioned this word before. It's myogenic, so it's generating its own electrical impulses. Okay, and this is what I've drawn or added on here is a picture of a battery there. That's known as the sinoatrial node. Okay, sinoatrial nodes are just up here. Okay, it's located at the top of the atria, towards the right hand side, I should say, anatomically speaking, towards the right hand side of the heart, just above the atria. And the job of the sinoatrial node is to receive these impulses. Okay, so the brain up at the top here. Okay, we have inside of the brain we have something called the medulla or the medulla oblongata, And inside of that, we have something called the CCC, or the Cardiac Control Center. And this emits impulses via two pathways. Okay, we have the sympathetic nervous system or the parasympathetic nervous system. Okay, so the sympathetic nervous system or the parasympathetic nervous system. Now, think of para as parachute. So a parachute slows someone who's jumped out of a plane down. It slows them down. So the parasympathetic nervous system is there to slow down these impulses, the frequency and the quality or the quantity of them. It slows these impulses down, causing the sinoatrial node to send less impulses across the atria, causing them to contract. The sympathetic nervous system, however, is there to speed it up. Okay, if we start to exercise and we're starting to get tired, we're starting to fatigue, our brain or our cardiac control center has sympathy for us, therefore it engages the sympathetic nervous system. This increases the rate of impulses that our brain sends to our heart. And the first thing which comes in contact with that impulse is the sinoatrial node. Okay, its job is to then transmit this impulse across the walls of the atria. So these electric bolts here, or these lightning bolts, okay, this impulse sent from the brain hits the SA node. It's then sent across or through the cardiac muscle surrounding both atrium. And the result of this is atria contraction. So they're now squeezing the blood out of both atria on the right and the left-hand side, squeezing blood out of the atria down through the valves and into the ventricles. Okay, we've now emptied the top half of the heart and we've filled up this bottom half of the heart. Okay. Now this impulse continues its journey and it moves so from the SA node across both atria, and then it arrives at the atrioventricular node. Okay, so the AV, can't we see that color there? I'll just go on to yellow. So AV node, or it stands for the atrioventricular node, and that's because it's based between the atria and the ventricles. So if we were to think of the heart as a very simple drawing, and here, if we've got the heart as a very simple drawing, so just a box here. We've got the atrias up at the top, or atriums up at the top, and the ventricles down at the bottom. The AV node is just here, right on that cross section. It's right in between. Now, the role of the atrioventricular node is to hold on to this impulse just for a second, okay, a split second, and it gives the heart enough time, the valves in between the atrium and the ventricles, to shut the valves up so that when the ventricles do contract, no blood goes back into the atria and the heart, starts to implode. Okay, so the AV node there, or the AV node is there to hold on to that impulse and to stop the impulse from carrying on further. Okay, when it's ready to do so, though, it passes this impulse down the septum of the heart. That's the separating column of tissue running down in between the two ventricles, and inside of that is something called the bundle of His. That's this phrase here in blue. So it passes this impulse down the bundle of His until it reaches the Purkinje fibers. Okay, Purkinje fibers. I like to think of these as if you were to, take a plant out of its plant pot, and you've got all of those tiny little white roots sort of nestled in and around the soil, around the surface, and inside that outer layer of soil. It's very much like these Purkinje fibers. We've got these nerves protruding out into the cardiac muscle surrounding both ventricles, so that when the impulse passes through them, it innervates, it excites this cardiac muscle, and it forces these ventricles to contract. And that's how our heart beats. Okay, so it begins up in our medulla oblongata, okay, where we have our cardiac control center. If we're exercising, we want to speed the heart up, then we engage the sympathetic nervous system, which causes the SA node to increase the frequency of its impulses. These impulses spread across both atrium, causing them to contract. blood's emptied out of the atrium as a result and into the ventricles. The impulse, meanwhile, arrives at the AV node, okay, which has the job of pausing this impulse, holding onto it, just so the valves in between the atrium and ventricles can slam shut and blood can't go back up. It then passes this impulse down the bundle of His, which reaches the Purkinje fibers, spreads out into the myocardium or the cardiac muscle surrounding the ventricles, which then also contract. Blood's ejected out of the heart up to the lungs or out of the aorta and to the rest of the body. And that's the cardiac conduction system. So, a lot of this information we sort of covered in that previous slide there. This just sort of clarifies the role of the SNS and the PNS. And from the diagram on the right-hand side, hopefully you can see that we've got more contractions of the heart when we engage the sympathetic nervous system opposed to the parasympathetic nervous system. Okay, so according to the data that's being received by the brain from all the different receptors around the body, which we'll do in more detail on a slide to come, because of this information, the brain is realizing that we need to increase cardiac output. We need to get more blood out of the heart to the rest of the body to make sure there's enough oxygen to sustain exercise, and we avoid the poisoning or the buildup of carbon dioxide and lactic acid. So in order to accomplish this, we engage the sympathetic nervous system, we increase the frequency and the quality of those impulses that arrive at the SA node. As a result, we get more contractions and more powerful contractions happening every single minute. So, chemical control. We've looked at neural, that was the sympathetic and the parasympathetic nervous system. We've looked at hormonal, that was adrenaline. We now look at chemical. Okay, and a large part of chemical regulation is to do with carbon dioxide, because carbon dioxide is a byproduct of aerobic respiration. And we have things called chemoreceptors. Okay, we'll do more detail on those in a slide to come. But we have things called chemoreceptors, which are located in and around our heart and our coronary vessels. Okay, and they're there to detect changing levels of carbon dioxide. So if carbon dioxide begins to increase, that suggests that aerobic respiration has also begun to increase. If we're starting to respire more, that suggests that our muscles are moving and working and demanding energy. Therefore, this information arrives at the brain, and the brain then decides to engage the sympathetic nervous system to speed up heart rate as a result. Because if we've got rising carbon dioxide, we want to get rid of it. Okay, carbon dioxide, when dissolved in the blood, it can form carbonic acid, and it begins to reduce that pH of our blood and our muscle and surrounding tissue. And if that pH drops too far, then we're actually putting ourselves at risk. Our muscles begin to fatigue, and we almost get carbon dioxide poisoning. So, aerobic respiration produces that carbon dioxide as a byproduct. As it does dissolve, we form that carbonic acid. It's inhibiting for the muscular function and its ability to perform. We start to feel more tired, but the chemoreceptors pick up this change in CO2 or this change in the chemical balance inside of our blood, relays that information up to the brain so that it can then decide to engage that sympathetic nervous system. Similarly, when oxygen levels start to drop, so another chemical change inside the blood, if oxygen begins to drop, then chemoreceptors pick that up as well. So if we are using it to respire aerobically, to break down and to reconvert lactic acid into a usable substance, then oxygen is going to be used up. We're going to form H2O at the end of aerobic respiration. Chemoreceptors detect this and send that message up to the brain to say, we need more oxygen around the body. So what's it going to do? Engage the SNS, or the sympathetic nervous system, to ensure that we've got oxygen traveling around at a far higher rate so that all of the muscles receive enough to sustain exercise. And there you go. That's just signifying there what's on the pictures. We've got the key ones here in the aortic chemoreceptor, or the chemoreceptor in the aorta. which is the main blood vessel carrying blood away from the heart to the rest of the body, and up here in the carotid part of our vascular system, which is up towards our neck. So, activities that I would like you to do linked with the work that we've just done. What's a hormone, or which hormone is available, or which hormone do we produce or secrete to increase heart rate just before exercise, also known as anticipatory rise. Explain the vascular shunt mechanism. What happens? How do we change our body? And why does it help? Then for the third question, how does a netballer regulate their heart to be able to cope with the physical demands in a game? So be specific about the neurological pathways, about the chemoreceptors, about the changing gases of oxygen and carbon dioxide, and then the cardiac conduction system, which actually causes the contractions of the heart. Then for the fourth one, the neurological response to carbon dioxide. So CO2 is going up, what happens? Okay, so 4 questions, give those a go, and I'll see you in the next part. Good luck.